Okay, so here is our data. And I'm just going to flip over to variable view here quick. Yep, I've already renamed those, so we're good to go. All right, the first thing that the videos and the chapter this week went through a few different aspects of regression, and the big thrust of this chapter is looking at independent variable sets, right? We're going to get to sets in just a second, but before we do, we're going to talk a little bit about coefficients and slopes, because I think it's important to understand slopes first in the context of what they really are, and then talking about slopes in the context of variable sets. So if somebody had a definition of an unstandardized slope, I've asked this in the past, what is an unstandardized slope?
Is it a change in y where there's one unit change in x?
Yes, for 1 unit change in x, what is the change in y that we see? That's a good way to describe it. In the video, I talked about some of the problems, especially in psychology, with using this unstandardized slope. What were the problems? Anybody recall?
Well, a lot of your times, not all your variables are on the same scale.
Yeah, well, it's often a problem of scaling, right? And it's not just different scales between x and y. It's different scales between like Mark and I. One person likes to use, a 4-point scale for something, and another person will use a 10-point scale, and another person will use a 2-point scale, and it makes it very difficult to translate back and forth between these different types of scales. This is actually why we've focused more, why the science in general has focused more recently on effect sizes rather than simple unstandardized coefficients. What is the benefit of an unstandardized slope? Versus a standardized slope?
So that you can make actual inferences, like scientific inferences about the unit changes?
Yes, it has true scientific meaning, right? You can make inferences about what you might expect on y given x at a very kind of precise point, right? Which you can't do with unstandardized, and that winds up being, or with standardized, and that winds up being the main drawback of standardized slopes, right? And so what is the benefit then of a standardized slope?
It's easy to interpret.
It's what?
It's easier to interpret.
It's easy to interpret because it means what? What does a standardized slope mean?
So basically, it's a simple regression equation, which is on the graph.
Yeah.
And it exactly tells the standardized slopes, the rate at which the y should increase with the slope, with the change in x.
Yeah. So if you were to describe a standardized slope the same way that we describe an unstandardized slope, how would you describe that?
Yeah. So it's not it's increase this, if one standard deviation is increased with the x, how much SP is increased with the corresponding y?
That's exactly what it is. What proportion of the standard deviation is increased in y, right? And if it's a 1-for-1, then you have a perfect correlation, right? If it's not, then you have a 1 standard deviation increase in x results in a point whatever standard deviation increase or decrease in y. It does place them on the same unit, which is nice. It places them on a standardized unit. What else? When you think of a standard unit, a standardized variable, what does that mean? What is a standardized variable? let's do something quick.
Sorry.
Yeah, go ahead.
So its mean is 0 of the standardized variable, and the standard deviation is uniform for among all the cases.
It's not just uniform, it is
one,
what?
it's one.
It's one. Yeah, it's one, absolutely. And we have a name for this, and it's called what? Yeah, Z, right? Or for my Canadians, Z. Or anyone who's not really from the US, it's Z, right? Is that right? You guys all learn it as Z? Okay, so let's do this quick, actually. Let's try something. Let's go analyze. Yes, I'm recording.
Okay, sorry.
Let's go analyze descriptives, explore, and let's throw all of these variables over. We don't need to throw drinker 1, 2, 3, 0 over. We're going to talk about those in a little bit. And you don't need to put PBS tot over either. Statistics, those are fine. We don't need to check anything else. Options, yep, that works. All right. Hit go. Move this over just a little bit. All right, so here's our basic statistics, 1,428 people, our variables. We have some missing, right? It has almost 13% missing. Yeah, right there. And here we have some of our descriptions of our variables. I didn't talk about this in the data visualization, but this is also a way to kind of check for your normality of residuals. Notice that when we look at descriptives here, we have a mean, and then we have a standard error of the mean, and we have confidence intervals, median, variance, standard deviation, so on and so forth. We can, if we come down here to skewness, we have for PBS harm, we have skew of minus 1.601 with a standard error of 0.065. So minus, what direction is that skewed? Is that skewed to the right or skewed to the left? Skewed to the right, yep, absolutely. And if you divide that minus 1.601 by 0.065, we get what? A z-score, yep. A z-score is just the any value divided by that standard error. And so we actually, if you do this, if you do a regression model like I did in the visualization video, and then you just grab the descriptives of your residuals from that, because you can ask SPSS, we'll do this in a second, to give you your residuals. You can divide those. You can take that skew statistic, divide it by your standard error, and that will give you a z-score of your distribution of residuals and tell you if you have significant skew in those residuals. You almost always will. Definitely you will with 1,400 people, right? Like the higher the sample, the greater the likelihood that any small deviations from normality will wind up being statistically significant. So in those cases, we often try and say we put a z-score closer to 3 standard deviations to determine whether or not we think that it's going to be have a significant impact. But we're not going to worry about that right now. My point of doing all of this is to look at this piece of it. So PBS harm has a mean of 3.9896 and a standard deviation of 1.43601. We can use those to compute a z-score for PBS harm. How do we do that? How do we compute a z-score? Anybody know? So we know that a z-score needs to have a mean of what? Of 0, right? And so in order to get a mean of 0, we need to subtract this value from our current mean, and in fact it winds up being from the current variable as a whole, right? And that will give the mean. If you subtract 3.9896 from every value of PBS harm, then you get a mean of 0. This is also called something else. Anybody know what? It's called centering. This is how we center our variables, right? We subtract the mean from every single observation. But we're going to go one step further. In order to get a z-score, we have to have a mean of 0. So that gives us a mean of 0. How do we get a standard deviation of 1?
Divide by the SD.
Divide everything by the standard deviation. So let's do that. Let's make PBS harm into a z-score. Let's go transform, compute. And let's call this z PBS harm. And let's say that it is PBS harm. I'm going to put some parentheses in here. Minus 3.9896, right? This isn't going to be perfectly 0, but it'll be pretty close to 0. And our standard deviation was 1.43601.
Can I just ask a question?
Yeah.
Isn't there also a way that you could have done like PBS harm minus the mean of PBS harm divided by the standard like, isn't that a...
It's like a function within here. Yeah, you can do that.
Okay.
For descriptive sake, I just want to go through it this way. But yeah, you absolutely can do that. And actually, it'll be more accurate if you do it that way. But yeah. Yeah.
Can you help me out this way, please?
Oh yeah. Whoop. Better? Are we all there? Yeah? All right. Let's hit OK. And now up here we should have a new variable, z PBS harm. And let's have a look at it. Let's go analyze, descriptives, explore. Let's remove all of these. We're going to scroll back up and use those in a minute because we're going to create another z-score. But and let's put z PBS harm in, and let's just make sure that it actually made it into a z-score for us. So we put that in, and we click OK. Our mean is now 0.0008, which is pretty close to 0. It's not exactly 0, right? Standard deviation 1.0213. Let's see if I can remember how to do this. If we go transform, compute, and this time instead of PBS harm, let's make a z-score of something else. How about, let's do audit problems. So I believe if we go audit problems minus mean audit problems divided by, do I put SD or STDev? Do you guys remember? Nobody knows?
Arithmetic all the forms.
Say that again?
With the arithmetic function group, either you can know with SD or yeah, arithmetic.
Not there. Can I do search? No. Statistical. There we go. SD. Does that have to be capital S? I don't know if it does or not. SD, audit prob. I think this will work. We'll give it a try and we'll see. Nope. Only one argument was supplied for a function
So
which
basically, like in mean, we need two variables to calculate their mean, not the average of the one variable.
Oh, yeah. Okay. Mean. Two or more arguments, which must be numeric. Yeah, so it's trying to give me the actual mean of audit prob. Okay. So I'm not going to do that right now because I don't know what I'm doing in SPSS when it comes to that. We will just use the old workaround way, which is the way that we built the first one. Let's do the same thing. Oh, we didn't look at PBS harm, did we? Z PBS harm. Let's scroll back up. It's right here. Oh, we did look at it. Pretty close to 0. And there is the stem and leaf plot. Obviously, it's heavily skewed. We knew it was skewed already. And there's our box plot with whiskers that you can see that it's quite skewed towards that direction. Let's do the same thing for audit prob. So we have a mean of 0.2907. And actually, if you click in the box and then you double click in here, it will allow you to get a much more fine-grained mean, I believe. Is that right? Not that much more, but a little bit. Okay, let's get rid of our pivot table and transform compute. We're gonna go Z audit prob equals audit prob minus, that was our mean, right? Divided by what? So I hear somebody saying it. No? 0.66243. And then let's just go analyze, descriptives, explore, and let's make sure that this looks like a good z-score. Z audit prob. Ooh, that's not the right mean. What happened there? Did I not subtract the correct mean here?
It looks like it's 0.2907.
Audit prob 0.2907. I'm going to delete this variable and we're gonna redo it. Transform compute. That's weird. Standard deviation 66243. Huh. That is something else. All right, so let's not use audit prob. Let's try a different variable. I don't know why that's happening. I mean, my guess is it's a, oh wait, it's only doing it on 40 people. Oh no, it's not. Oh, it's, oh, so it's, yeah. So, this is what's happening. Do you guys, who knows what's happening? Go, descriptives. Let's do this, actually. Let's troubleshoot this. So this is a good point. Sometimes we run into problems and you've got to figure out exactly what's going on. If we go analyze, descriptives, explore, and we put in just audit prob over here, and we hit go. What was our mean before? 0.29, and what is our mean now? 0.35. Why? What's going on here? This is why I hate SPSS. That's what's going on. So what's going on is SPSS doesn't pull all of the data when it gives you this per observation. It deletes cases list-wise. And that means that in the original one, we had a bunch of different variables, and it will remove data, actual data, even if it's missing on any one of those variables, right? So if we had data for PBS, for audit prob, but we didn't have it for PBS harm, it will delete data for audit prob. It removes listwise across so that your sample is consistent. So you can see here, our missing observations for audit prob were only 40. However, if we come up to the very first thing that we ran, our missing were 220, right? This becomes important when you're centering, and there's a reason that SPSS does this. It's because if you're going to center, you should center across just the variables that you're going to use in your analysis, right? And so that you have a consistent N within your model. So this is the problem that we're running into here. Let's do this. Let's just figure out I'm going to remove the two z-scores that we created. And let's just look at the variables that we want to use. So let's go analyze, descriptives, explore. We're going to look at audit prob. Let's do PBS harm, and let's do urgency. Those are fine. You can actually change your listwise here. You can change it to pairwise or report all of the values. We'll leave it as listwise for right now. So we put those three variables in, and here's our new mean, 0.2953. And 0.39953. And 1.96555. You know what? Just to make sure, let's do this. Let's go data, select cases if. I wonder what the thing is that we're actually missing. So in this report, how much missing did we have? 200. Data, select cases, if, let's go, I'm guessing that it's, let's go harm is not, how do we do missing in here? Is it just dot? Let's see if this works. No. Let's go PBS harm. It's greater than 0, and audit prob. It's greater than 0, and urgency is greater than 0. All right, so now we're going to be playing with the same data all the way across. And now let's go our analyze. Yes.
We couldn't get we got to select cases, but we couldn't get the box when entering the equation.
You need to see it again. Did I go too fast? Is that the deal? So select cases if
Clicking on it.
PBS harm is greater than 0 and audit prob is greater than 0 and urgency tote is greater than 0. What this actually does is it eliminates anyone who has no alcohol problems as well as the other things. So see, a lot of people don't have any types of alcohol problems, which is fine. All right. Now let's go analyze descriptives, explore. We're going to look at those 3 variables again and hit OK. We have new means, so now let's use these means. And let's go transform, compute, z audit prob equals, what was our mean here? 0.7297. And our standard deviation was 0.91641. What's invalid?
You just need to.
Oh, I deleted this. My mean here. What was the mean again? Somebody looking at it? 7297. Okay. Let's make our next one, which was PBS harm. So transform, compute. PBS harm. Our mean for PBS harm was
4.1305.
say that again.
4.1305.
5. And our standard deviation was
1.0097.
Z PBS harm.
Just remove the point from before the point.
Oh, thank you very much. .1298. Ah, dang it. All right. Transform, compute. Urge tote. 2.1298. Are you guys already done? Is that the am I way behind you? 60352. Z urge tote. All right. Are we all there? Everybody got those? At least urgency looks pretty decent as far as normal distribution, right? Okay. Are we all ready? Are we there? Okay, let's do something real quick. Let's go analyze regression, linear, and let's put in audit prob as our dependent variable. And then let's put in PBS harm and urge tote as our predictors. And let's hit OK. We just ran a regression model that is looking at PBS harm and urgency as predictors of alcohol problems, right? We see that about 6% of the variance is accounted for by this entire model. The model does have a significant F value. That means that there is some variance accounted for within it. Oh, you know what? I didn't select, oh, the beta coefficients are already there, so we're good to go. All right, so how do we explain this? What's going on here? Who wants to take a stab at describing what these things mean?
So you can see that both PBS harm and urgency are significantly related to audit prob.
Good. Or using the language of regression, right? They significantly predict audit prob?
Significantly predict audit prob with p-values of 0.000 and 0.046.
Yep.
PBS harm is negatively related to audit prob, and urgency is positively related, as shown by the unstandardized beta coefficient and the standardized beta coefficient.
Yes. Let's do and we don't need to talk about magnitude or anything, but let's do something else now. Let's go analyze, correlate. Actually, let's not do correlate. Let's go analyze regression, linear. Let's remove audit prob, PBS harm, urge tote, and let's put in our z-scores now. Z audit prob, Z PBS harm, Z urge tote. Hit OK. We're going to just scroll right down here. Our constant is now essentially 0. Why is that?
So the regression line passes through the 0, 0 point.
Yeah, so
There is no residual.
in a regular regression graph, right, we can have a line that goes like wherever, right? But in a correlation table, you always start at this corner and it kind of fluctuates from there when you're using standardized variables, right? Because you've set the means for both variables to be 0, right? So, all right. Now our slope is minus 0.205 and 0.082. Those are different than what we got up here, right? Not the same, but they're exactly the same as standardized coefficients. Why is that? What's going on here? Why is it if we change these to z-scores, they become the unstandardized coefficients become the exact same thing as a standardized coefficient? This goes back to something that we talked about last class.
Because the z-scores perfectly fit the line.
No, not quite.
Maybe I'm not saying this. Like, yeah, I'm not
Let's
gonna be able to
let's think about this for a second. How did we, so in the first regression analysis, we are looking at unstandardized raw data, right? And we used that unstandardized raw data last class to calculate a correlation. And what was the first step in calculating a correlation? Remember, I gave you guys this whole long formula to calculate a correlation coefficient, and then I said, but there's a much easier way to do it, and the first thing you have to do is what?
So we have to standardize the Cx to Cy and divide by the n minus 1.
Yeah, so by standardizing it to Zx and Zy, what are you actually doing?
So
You're making those variables into
the standardized
Z-scores, right? Yeah. And so it's the exact same principle, right? A standardized regression coefficient is just the correlation once you've transformed both of your variables into Z-scores, right? In an unstandardized regression, we have slopes with some sort of meaning. In a standardized regression, essentially what we're saying is this is a relationship, assuming that we were to make these things into Z-scores. There is a whole school of thought that has tried to transform regression into all Z-scores, because at least then everything is on the same scale. You don't actually have to transform anything into Z-scores if you don't want to, because you do get standardized coefficients when you run a regression model. One of the benefits, though, of using a Z-score is it always provides you with a centered variable, which makes understanding interactions a little bit easier, right? But we'll get to that later. That's probably beyond what we need to talk about right now. Yeah, go ahead.
So in other words, the Z-score will standardize both predictor and outcome variable.
Well, I mean, you're standardizing your predictor and your outcome variable by making them into a Z-score, and so the relationship between the predictor and the outcome are standardized. Yeah. All right. You know what? Let's take a 10-minute break, and then when we come back, we will dig into the next portion of this, which is looking at sets.